Count me in. Okay. Good evening, everybody. Welcome to our Amateur Astronomers Incorporated meeting, and we have a guest speaker, Matt Garrison from the Goddard Spaceflight Center. Matt has worked at Goddard for almost 20 years. He graduated with a Bachelor of Science and Master in Science in Aerospace Engineering from Penn State University. At NASA, he's worked as a thermal engineer and systems engineer for multiple science missions, including the James Webb Space Telescope, Lunar Reconnaissance Orbiter, ICESat-2, Lucy, and DAVINCI. And he's currently serving as the lead engineer for DAVINCI. And now, welcome, Matt. Thank you.
Hey, John, thank you so much for the intro. And sorry I couldn't be there in person. Would have been nice to be able to do this. I had my train ticket all booked. Maryland is really bad at snow, and we got about 5 or 6 inches today, so most of our area is shut down. So even if the college had been open, I would have probably not been able to make it. So give me a second to share my screen, and we can hop in. All right, can someone confirm you can see that?
Looks good.
Yes, it looks good.
All right, cool. Well, thank you so much again for having me. Just a quick intro on me, and then I'm going to talk through our 2 most recent planetary missions down at NASA Goddard. So I grew up in State College, Pennsylvania, which is right in the middle of the state, about halfway between the Eagles fans and the Steelers fans. So just to give you a sense of location. Growing up, I didn't really have any particular interest in space, other than space Legos were really about it. So it was kind of a lucky coincidence that I ended up in this career that I really ended up enjoying. So I just grew up enjoying reading, running. I enjoyed school. I think this career kind of self-selects for people that are a little on the nerdy end. As I mentioned, I got my BS and MS in aerospace engineering at Penn State. Growing up in State College, and especially with a parent that worked at the university, getting faculty discount on in-state tuition makes that an easy option. And you still have a lot of family up there. So we actually have the same football season tickets that I've had since I was 5. And now my wife and I go up for 5 or 6 weekends every fall to go to games. So as I mentioned, I graduated in 2005 and I went straight down to NASA Goddard. So it's about 2 miles outside of the DC Beltway. I started as a thermal engineer working on spaceflight missions, both spacecraft and instruments. I eventually moved into systems after 12 years, and that's what I'm doing now. So we mentioned a few things I worked on. I worked on the James Webb Space Telescope.
Astronomers Incorporated for our weekly presentations that we.
Sorry, I've got a live mic back there. I did work for James Webb Space Telescope on near spec for a little bit. I worked on the spacecraft for the Lunar Reconnaissance Orbiter, which we launched in 2009 and is still going around doing some great imaging from the moon. ICESat-2, I led the thermal team for the instrument. So this is a polar orbiting laser altimeter that's measuring surface heights to within about 5 millimeters, using it to create good topographical maps, track ice sheet melting, things like that. And then I made the pivot into planetary science. And those are the missions I'm going to talk about here tonight. So first, I worked on Lucy, and now I'm working on DAVINCI. Before I get to that, though, Goddard doesn't usually have a high profile when it comes to planetary missions. You usually tend to think of the Jet Propulsion Lab for that. But we've been getting involved with them lately. We ran the MAVEN mission, which is still going around Mars, OSIRIS-REx, then Lucy, and now DAVINCI's our 4th in a series. So before I continue, I did want to share quickly, they just today released the photo. This is the sample capsule for OSIRIS-REx. This is the pieces of the asteroid Bennu that we brought back to Earth, dropped in the Utah desert, I think in October. And unfortunately, the lid had been stuck on with a stripped screw for a few months before they were able to design a special tool to remove it and get that open. So this is the first publicly released image of the samples from the asteroid Bennu that are now sitting in a curation lab at the Johnson Space Center. So really excited to see that. So I'm going to start first talking a little bit about how the Lucy mission, which is currently flying around the solar system, and then I'll pivot to talk about DAVINCI. So Lucy is a tour of the Trojan asteroids. So these are the set of asteroids that are in the Jupiter L4 and L5 Lagrange points. So these are these stable gravitational wells that lead and lag Jupiter in its orbit by about 60 degrees. They're a really interesting sample for kind of the relic of the early solar system. They're far enough away from the sun that a lot of the volatile chemicals that might have already been outgassed on the main belt asteroids are still assumed to be part of these. And because they're a good gravitational well, it's a fairly pristine area. So it's something we're interested in. We want to study it. It's a lot harder to get to than a main belt asteroid. So we haven't really done any up-close study of these asteroids in the past. This whole mission is enabled by a really cool trajectory that the flight dynamics team found. So we'll walk through it quickly. We launched in 2021, and in 1 year we did an orbit of the sun and came back to do an Earth flyby. This gave us a little more orbital energy and it sent us out further out. This is the leg we're on now. So flying out a little bit past Mars distance, and then we come in, and in late 24, we're gonna do a second Earth flyby, and this will give us the last bit of oomph we need to kick out on this long ellipse. We're gonna pass a main belt asteroid called Donald Johanson. This wasn't really part of our science campaign. It's just it was a lucky coincidence that we're passing by one. And it gives us a chance to kind of practice what our encounters look like. So it'll be a good opportunity to try out the instruments, try out all the pointing, and be ready to go when we hit the main belt, or hit the main L4 and L5 swarms. So we continue on this big ellipse, and we essentially, as we get as far away from the sun as we're going to get, we're kind of slowed down, and the Trojans actually catch up and pass us rather than us flying by them. So we pass a few to begin with. Euripides and Keta is its moon. Polymele is a small one that we pass soon after that. And then we get Lucas and Oris. Just for anyone who's following along, these are the Trojan asteroids. These are all named after the Trojan characters from the Odyssey and the Iliad. The L5 swarm are the Greeks. So we encounter these four, and then we fall back down towards the sun again. We interact with Earth one last time. This is less to give us more orbital energy and more to steer us so that we come out to the L5 swarm and get to pass a binary system of Patroclus and Minutius. So these are two similar sized asteroids that are orbiting each other, and we'll get to go fly by those. And then that's essentially the end of our mission. We're going to continue just on these long elliptical orbits, and if everything's still working fine, we'll see if there are other targets nearby. But this is the length of our mission. You'll notice I said we launched in 2021, and the mission ends at the end of 2033. So this is a 12-year mission. So it's a lot of work to get a spacecraft and a bunch of instruments that are designed to be able to survive for this long. So this is what the Lucy satellite looks like. So it took about 500 people when it's all said and done to design, build, and test this. Weighs about 3,000 pounds when fully fueled. And it's got a really robust thermal design because we've got to have something that can work when you're out at Jupiter distances, but also is fine living at like the 1 AU Earth distances to the sun. This is also really big. It's about 4 stories tall when you set it on edge. And of course, the big thing you notice here is these massive solar arrays. When you're a solar-powered spacecraft at Jupiter distances, you've only got about 1/35 of the amount of sunlight you get at Earth out there. So you need a lot of area to gather enough energy just to keep the spacecraft running. So that kind of summarizes what we're studying, what this trajectory is. I'm going to walk you through a few photos of the process of building and testing this thing, and then going into launch. So the primary instrument came from NASA Goddard. That was the instrument I was in charge of. We'll talk to that one in a second. The actual spacecraft was built by our partners at Lockheed Martin in Denver. So this is part of a series of satellite buses they've built for us. They're all kind of built on the same heritage. You know, everything's a little new and a little unique each time, but it's got the same central core of what makes up their spacecraft. So you can see on the left here, this big high gain antenna that we need for those transmission over those long distances. And on the right, you can see a picture of the satellite on a turnover dolly, tipped horizontal to get access to the reaction wheels, which are these little black circles over here. And the instrument pointing platform is on a dolly over here. So as we're flying by one of these asteroids, you've got all the instruments pointing in the same direction on a platform that has a 2-axis gimbal, so that autonomously the spacecraft can find the asteroid and gimbal this platform around to keep it in the field of view of all the instruments while we're doing a flyby, so that we can make sure we're getting the most observations. This is a picture of me in front of the instrument I've put together. So the primary science instrument on this is Ralph, which is based on the Ralph instrument on New Horizons. So it's a dual channel, it's a near infrared visual imaging spectrometer, and then a 6-color push broom visible camera. The imaging spectrometer is, of course, the heart of this, because it's what lets us determine, get spectra for individual points on the asteroid and figure out its composition, but also look if there's any variation in composition. And one of the things we're really excited to look at is look for impact craters and see if the material on the surface inside the impact crater is different than what's on the outside, because that might give us an idea if there's any layers or kind of strata to the asteroid. So once this all got built up and assembled, here's me and 2 of my friends standing in front of the satellite, and this round disc here is the big radiator on top of my instrument. As I mentioned, the solar arrays were a big part of this, and if there's one thing you know about Lucy after its launch, it's that the solar arrays didn't quite do what we hoped they would do. In fact, sorry. So if you see it's unfurling, there's this cord that kind of connects it and pulls this around. So what happens is after launch, the solar arrays flopped down, it started pulling in that cord, and that unwound both solar arrays, and it pulls it into a latch, and then the motor pulling in the cord cuts off, and it's all stable and good to go for the next 12 years of mission. So it turned out that one of those cables came off its spool and actually bound the axle. So it took a few months of working with the operations team, testing things out on the ground. They were able to get that second array, the one that didn't quite deploy right, open about 98% of the way. So unfortunately, what that means is for the next 12 years, rather than having this thing securely in a mechanical latch, we're counting on the tension of that cable to keep the solar array open. Now, it is a tensioned Kevlar cable. It's incredibly strong, and it's used for much more rugged stuff than this. So we think we're in good shape there, but more importantly, there's nothing more we can do about it. So that's, yeah, it was a bit of a nail biter. Most of us who weren't on the operations team didn't know anything had gone wrong until about 12 hours after launch. And it was a tense, 6 or 7 months while they were working on this, before they kind of got to a point that they think we're in a good, stable position. So we built up the instruments at NASA Goddard. We shipped to Denver, where we built up and tested the whole satellite. Then we came down to Florida for a launch. This is a picture in the Astrotech integration facility right outside of Kennedy Space Center. And this is the last anyone gets to ever see of the spacecraft. There are no access doors in the fairing. So we got one last chance to look at Lucy, and then they seal it up, and that's it. The next time last time it gets to see any light will be after launch when the fairing comes off. That assembly gets put on a truck, shipped into Cape Canaveral, and we were launching on an Atlas V. So this is a very tall, very slender building with kind of horizontal garage doors that open up. And this whole fairing assembly with Lucy inside gets lifted up to the top level and brought over to the right here where the rocket is sitting waiting for it. Once it's mounted, that whole thing gets rolled out on a pair of train tracks out to the launch pad. So this is the view from that patio. So basically standing right here, looking out of the launch pad with the rocket there. And then way too early in the morning, we all went into Kennedy and got to go watch a really perfect launch. The weather behaved, the spacecraft and the rocket behaved, other than that solar array that we talked about. And right at the beginning of the launch window, it went off. So it's always a really cool experience to get to see these. It's unnerving to spend 5 years of your life working on something, doing long hours, weekend and night shifts, and then put it on top of a rocket and hope it doesn't explode. So it was good to see that go up. And of course, one of the things you might have seen, this was in the news recently, is we actually, after launch, found there was another asteroid in the main belt that we were passing really close to. It's named Dinkinesh, which is actually, I believe it's the Ethiopian name for the Lucy fossil. And so we actually got to practice a flyby of that prior to Donald Johanson. So this really kind of shook out everything and showed everything worked really well. And it was actually really neat that we didn't realize until we did this flyby that not just is it an interesting asteroid, it has its own satellite. This picture shows its satellite about to go around behind it while it's orbiting. And that satellite's actually a contact binary. You can't see it in this picture, but the satellite is actually two big lobes. It's two big rocks that kind of just stuck together at some point. So it's really interesting, really dynamic. If you're ever interested in what's going on with Lucy, whereislucy.space is a website that our partners at the Southwest Research Institute put together. And it lets you see where it is relative to all the planets. So green is Earth, yellow is Venus, red is Mars, and here we are. We've just passed Dinky, and we are on our way back down before we head out towards the fourth Lagrange point swarm. So now I want to pivot. That was the third in the series of NASA Goddard planetary missions. And so now I want to talk to the fourth one, which is DAVINCI. This one is really unique for Goddard and for NASA in general. This is a whole different beast compared to a lot of the space missions we work on. I've got a pretty big team in there. I need to find a better picture of myself to put in there, but the main reason we're interested in studying Venus is we're interested in studying planetary habitability. Venus is very Earth-like in terms of its geology, in terms of its size. It's closer to the sun, but it's not that much closer. But it's a really horrible place. It's really dense, a lot of carbon, or really dense atmosphere, a lot of carbon dioxide, which, as you know, is a big greenhouse gas. And that just set up a runaway greenhouse effect there. So although it could have been an Earth-like planet, and maybe at one point it might have been, it has evolved in a way that it's just unrecognizable as an Earth analog right now. So we want to be able to study what happened and why that occurred. We were actually selected in partnership with a second mission from Jet Propulsion Lab called Veritas. So Veritas is going to do a high-resolution radar mapping of the Venus surface. We are trying to study its atmosphere, its chemical composition, and look at its geology and topology on a very small scale. Also, this ties into James Webb a little bit because all those clouds that surround Venus are really reflective. And what that means is if you've got planets that are really reflective and are close into the sun, they're going to put out a lot of light. And so it means that any Venus-like planets around other stars should actually be pretty detectable to James Webb, or to the Future Habitable Worlds Observatory. So we want to be able to study what's happening with Venus so that we can better understand what happens with those planets when we find them around other stars. In fact, we're a principal investigator-led mission. So it's 3 scientists who really are in charge of this, and one of them is actually looking at this purely as she's a expert in remote sensing of exoplanets, and she's looking at this as an analog for those exoplanets to try to figure out what we can learn about them by studying Venus. So importantly, Venus is really hard to study. We only have 4 pictures ever of the Venus surface. These were all taken by the Russian Venera landers. So the Russians did these in the 70s and the 80s. Highly successful Venus exploration program. They also, is one of my favorite parts of this, as part of these, they also had a high altitude balloon program that had, these were small, basically meteorology payloads hanging under balloons that had direct communication to Earth at 4 bits per second, which I keep, when we're giving tours, I like to remind people that you can clap at 4 bits per second. It's not even that fast. So the data stream back from then was really sparse. But yeah, this is all we've seen of the Venus surface. Everything else, any other maps you see are radar images, usually from Magellan. So we've studied Venus. We have some flybys of it. The Japanese Akatsuki has been really successful studying Venus, doing remote sensing. We mentioned the Vega balloons, the Vega and Venera landers. They landed and they did some study of the surface, but they didn't do any particular study of the atmosphere on the way down. Now, NASA had the Pioneer Venus probe program, which attempted to study the Venus atmosphere. Unfortunately, it developed a clog in the cloud layer about roughly 30 to 40 kilometers above the surface. And so the port where they were trying to ingest gas to take measurements was clogged, and they basically didn't learn anything below about 30 kilometers. And because of the kind of way that the atmospheric pressure builds over time, or over altitude, that means there's about 75% of the atmospheric mass that no one has ever measured. We're still trying to figure out what it's really made of and what's kind of driving this. So the DAVINCI mission is aiming to study that whole column of atmosphere all the way down to the surface. I mentioned the Magellan radar maps. So just to give you a sense also, if you go back to those images from the landers, you see everything's relatively flat and nondescript. The Russian landers all picked these flat rocky terrains or plains, which you kind of see in blue here, to do their landing sites. It's always easier if you're going to try to land somewhere that is flat. But what that means is there are these really interesting mountainous highland areas called the tessera that we haven't gotten to image. We haven't gotten to see anything of. So we're actually intending to land or descend our probe over Alpha Regio. So this is an area that's about the size of Australia. It's really mountainous highlands, and so it's interesting from the geological point of view. Provides a lot of engineering challenges in the process.
Matt, I'm sorry to break in. Is there a way that you could close the little strip on your screen that says you are sharing?
Yep. Sorry about that.
No problem.
Cool. So this mission, it happens in 3 main phases for science. The first 2 are Venus flybys. So we could do a direct launch to Venus. It's called a home and transfer. But the problem is if you do that, you interact with Venus going really fast. Faster means the heat shield has to absorb more heat, makes it that much harder. So we do 2 flybys of Venus in order to bleed off orbital energy. It also gives us a chance to kind of do some remote sensing. So our satellite is going to have two different instruments on it. One is a suite of cameras that look in the near infrared and UV. The UV we can use to study cloud motion as we're looking at the daylit side. The near infrared cameras are actually designed at band passes that allow us to look through the clouds and actually look at maps and composition of the surface through the clouds. Our second instrument is actually a tech demo called QVIS that we're developing at Goddard, and it's a dual channel spectrometer. It's a tech demo, so we get to be a little more sporty with it. One of the things we're trying out with it is using freeform optics. So that's basically, that's using mirrors that have non-circular or non-parabolic shapes to them. They're harder to make, they're harder to align, but they allow you to shrink the optics packaging a whole lot smaller and maintain the same resolution. The other thing we're doing with it that I think is really interesting is we're going to use, actually it's a Google provided AI processing chip. So Google has an algorithm where you can feed its chip 1,000 pictures of a dog and then send it a bunch of photos and say, tell me which one has a dog in it, and it'll find it. So what we're going to do is train it on a whole bunch of spectra of interesting molecules that we're looking for. And then when we fly by, we'll take all this data and we'll see if this can identify the particular images or the particular spectra that show the molecules we're interested in and flag that to download. This is a nice feature for us. It's actually something we're really trying to prove out for things that are going out to like the outer solar system, where the data link is that much harder to get a hold to use, because a lot of spectrometers, particularly imaging spectrometers, are big data hogs. So this will really enable really good spectral study for missions to the outer planets. Then the third time we interact with Venus is when we actually have our probe mission. And so that's the real heart of this. If all these flybys, if those went away, that's fine. The whole purpose for DAVINCI is to drop this probe into Venus. So we've got a handful of instruments that we're using to study. I already talked about the cameras and QVIS on the carrier. The probe is actually packed tight with these. So this is it's a titanium sphere that's about 1 meter diameter. So picture one of those big exercise balls from the gym. And it's got 5 instruments in it. We have a mass spectrometer and a tunable laser spec. These combined are essentially the primary science instrument on Curiosity. So we're taking them, we're updating them, and then we're going to fly something like the Curiosity camera or instrument suite on our probe. We have an atmospheric structure investigation. So this is essentially temperature sensors, pressure sensors, accelerometers, and gyros to try to map out the lapse rate of the atmosphere as we descend, try to measure winds, things like that. And then really interestingly, there's a big sapphire window on the bottom of the probe, and we've got a camera that's looking down through it to do descent imaging. There are 2 things we can do with that. There's a narrow band and a broadband filter, and ratioing those 2 images together, we can make a composition map and look at emissivity variations on different surfaces. It basically lets you see the difference between light rocks and dark rocks. There are 2 predominant theories on what the main rock types will be in this area, because it's kind of a raised continental shelf, but in a very volcanically active planet. So this will let us distinguish between more volcanic-looking rocks and more granite-looking rocks. And finally, VFOX is essentially the oxygen sensor in your catalytic converter in your car that's going to be hanging out outside of the probe. But this is fun because it's actually a student experiment. So this is being designed, built, and tested by a group of undergrad students at Johns Hopkins University. In fact, in 2 weeks, I'm going up there to talk to them and give them a quick class on requirements and risk management on planetary missions. So, when we go back to Lucy, we had this whole massive project with 3 primary science instruments on it. We're running a smaller, leaner project, and we've got 7 different instruments to give us kind of some good instrument science data return. over the course of the mission. Really quickly, Venus is horrible. It's a terrible place, and that provides a lot of interesting engineering challenges for us. First of all, when we hit the atmosphere, even going as slow as we are, we're still decelerating at 38 Gs. So just for reference on that, my little HP laptop weighs over 100 pounds at a 38 G deceleration. By the time you get down to the surface, it's 900 degrees Fahrenheit. That's more than enough to anneal aluminum. And a good restaurant quality wood fire pizza oven runs at about 900 F at the back. And at that point, a pizza cooks in only 1 or 2 minutes. I mentioned this really thick cloud layer. So that makes it hard to sense things. But also, it turns out the clouds are 75 to 85% concentration sulfuric acid. Sulfuric acid famously eats a whole lot of things. This is about 3 times as much acid concentration as you need to etch steel in industry. It turns out almost every polymer that you use to make parachutes will get eaten by sulfuric acid clouds. So we're working through that effort right now. And finally, by the time you get to the surface, we are at 95 bars of pressure, so about 95 atmospheres. At that point, carbon dioxide is supercritical, which means it actually is somewhere between a liquid and a gas. It makes the aerodynamics really difficult to work out at that range. It's the similar pressure to about 1 kilometer below the ocean surface. And then I mentioned, we're descending over these rocky highlands. When you look at the topography of that, it's actually really similar to either Yosemite or Great Basin National Park. I'm trying to find a way to get the National Park Service interested in having me go to those on the government dime. I'd love to get an opportunity to that. So, picture this picture of Great Basin National Park, only obviously no trees, 95 atmospheres of pressure, choking sulfuric acid gas, and it's 900 degrees. So yeah, not a great place to be. And that kind of drives us to how we're going to have to study this, which is, in comparison to the Mars rovers, Curiosity, I said it's a good comparison point for this. Curiosity lands on the Mars surface, and it spends a day fine. It goes to a new spot, then stays there for a few days and patiently checks, takes measurements, sends data back to the Earth. Earth decides maybe we're going to take a little more data, maybe we're going to go somewhere else, and it's been doing this for years because it can. We don't have that capability. Nothing we can make is going to be able to survive on the Venus surface for long. Even those Russian landers, I think the longest one ever survived was about 2 hours. And the way the Russians did it is they pumped down and pre-cooled everything before it entered, tore through the atmosphere as quick as they could, landed, and then just tried to operate until it died. We are not going to try to land. We're doing all of our science as we descend through the atmosphere. So we come in a entry vehicle that opens up when we're about 70 kilometers above the surface, and we come out under a big parachute. From 65 kilometers down to about 40, we are taking measurements with our mass spectrometer and our tunable laser spec, figuring out what the upper atmosphere is made out of. And then when we get to about 37 kilometers, we cut the parachute and we just free fall. At this point, our little downward facing camera starts taking its pictures, and we continue taking gas measurements down to the surface. So this means we're not going to try to land, but it means that we need to take all of our required science data and uplink it to our satellite that's flying overhead. It's going to act as a relay in 1 hour autonomously. And whatever's on our data recorder when we hit the surface is probably lost. We don't have landing gear. We're not going to try to land. If we happen to survive landing, we are still a metal ball falling window first onto a rocky highland. At some point, we will overheat, our battery will drain, or our relay satellite's going to go below the horizon, or we're a ball in a Rocky Mountain area. We may just roll and end up with our antenna pointing the wrong direction. So it's really interesting from a team dynamic point of view. So we're going to spend 8 or 9 years working on this when it's all said and done. We'll launch it, and the primary science mission is 1 hour where we have no control. We're not going to even see whether it was successful or not until the satellite turns back to Earth and starts sending data our way. And at that point, our probe is now going to be a smoldering wreck on the surface. So that's kind of the quick intro to what DAVINCI is. Right now we're kind of wrapping up our requirements reviews. So we're making sure that everyone knows what the components they're making need to be able to do, and beginning our preliminary designs. We'll get confirmed by headquarters it'll either be late 25 or early 26. And then we'll be launching in 2029, and 2 years later in 2031, we'll have Venus entry. If you go back to Lucy, which we launched in 21, Lucy will still have 2 more years to go on its mission by the time we do this. So the time frame for this will be really interesting, a little bit different than what some of us were used to. And that's really all I had to talk through. So thank you all for your time, and I'm more than happy to answer any questions or talk about anything you're interested in.
Thank you, Matt. That was wonderful. If people have questions for Matt, they can unmute themselves and ask. So, anybody with questions?
Yeah, Matt, how you doing?
Good.
Nice, very nice presentation.
Hey, thank you.
How do you think Penn State will do next year?
So how do we put this? We have a tradition of having high expectations, and if we get 10 wins, that'll be fine. I will say, so being in the DC area, let's see, we get the joy of playing off a lot of the Michigan and Ohio State fans. They are pitching a new DAVINCI logo where that probe is on top of one of the eyes, and the Ohio State people love the idea of this being dotting the I. So we're doing what we can to avoid that.
More on a serious note, are you testing the or measuring the magnetic fields in Venus?
No, we are not. I believe Akatsuki did that for JAXA, but no, that's not something we're going to be measuring. It's not something that I believe Veritas is looking at either.
Yeah, Matt, great presentation. Very interesting.
Thank you.
Question. Why do you cut the probe away from the parachute and let it free fall?
So that's you would think if the time in atmosphere is the interesting the thing that lets you study it, you would want to stay on the parachute as long as you can. The problems are, well, one, we've got that relay satellite, and 17, it takes us an hour to follow the atmosphere as is, an hour and 17 minutes. So just 17 minutes after we're going to touch the surface, that relay is going to go below the horizon. On top of that, the longer we're in the atmosphere, the harder it is to survive the temperatures, the bigger a battery we need. And I kind of mentioned this earlier, but by the time we get into that cloud deck, all the polymers that you make parachutes out of traditionally start dissolving really quickly. In fact, we just wrapped up some testing up in a facility in Baltimore that showed these, standard parachutes for a lot of these missions are made out of a polyester film. And it gets down to like less than 5% of its strength after the exposure to the acid we're expecting. So even if we wanted to go further on the parachute, even if we could design the probe to survive it, the parachute material just wouldn't allow us to go any further down.
Bill,
Matt,
you have
are
your hand up?
you?
Hi, Matt.
Are we
We raise
partnering
our
with
hands
any
if we're
other?
gonna talk.
Bill
So,
first, then
my-
Marcus.
Partnering with any other organizations like ESA?
So not on this, well, not any international organizations here. So NASA Goddard is running this. Jet Propulsion Lab is providing one of our key instruments, the tunable laser spec that someone just posted in the chat about. Some of our camera systems are coming from Malin Space Science. There's another S in there, I can't remember which. You'll know Malin from doing almost every planetary camera that's ever been done. Most of the ones on the Mars surface are them. Juno Cam was Malin. So they're doing all of our cameras. We mentioned Lockheed's doing our spacecraft, but we're not partnering with the European Space Agency, JAXA, Canadian Space Agency. On these smaller missions, and small is relative, it's about $1 billion-ish. It's usually easier if you can avoid international commitments, because those tend to end up adding complications in the project, both technically and financially and personally. So no, we're a US only effort.
Thank you.
Bill?
Yeah, thank you. Bill Griffith here. Matt, that was very interesting talk. Whoever made your slides deserves a lot of credit as well. It's really very professional and informative. My question,
those are about 3/4 me and 1/4 one of the scientists in charge who
really?
does outreach like no one's business. It's great.
Well, they're tremendous. But my question is about back on Lucy. You described the orbits, the orbit that you're taking with multiple flybys, and you apparently can predict the orbits of these individual Trojan asteroids with a great deal of accuracy. And that because it's complicated because not only are they in orbit around the sun, but they're in orbit around the Lagrange point, as I understand it. And you indicated that two of them were in orbit around each other. And so it's extremely complex, the orbital mechanics. It makes the three-body problem seem trivial. So
Oh yeah.
how is it that you're able to cope with this orbital complexity?
So the lead scientist on that, he was a theoretician. So this is his first real delve into practical hands-on science. But all of his theoretical work was on planetary system formation. So tracking how these things move, how they interact, that's his whole career. Fun story with him. So it's impressive how well they know these. And one of the things the scientists did while we were developing the mission was set up stellar occultation studies. So they would go predict that, let's say Lucas is going to pass between the Earth and a particular star at a particular time and cast a shadow on the Earth in a particular spot. And they would go out and put ground-based telescopes in an array in that area. And based on the light curves, they could actually measure the size and shape of those asteroids to that much precision. Now, the problem is you don't get to control where that happens. And so they ended up doing some stuff in Africa and everywhere else. They did have an instance of getting pulled over by Border Patrol because one of these stellar occultations happened right on the southern border of Texas. And so the scientists got there and, before night, they wanted to get stuff set up. So they drove around and started dropping off big Pelican cases full of equipment in different spots. And, someone saw it and called Border Patrol, and they had people showing up thinking they might be drug runners. So,
well, that's amazing.
The precision behind some of that stuff is amazing.
Yeah, I thought that chaos was a big factor in long term in any prediction of even planetary motions in the solar system. And you think that in the Trojan area that chaos would show up a lot sooner.
Yeah, don't know what the time constant would be on something like that though. So the mission concept and that trajectory was found about 20 years before the end of mission. So maybe on a solar system type scale, that's quick enough that doesn't matter.
Yeah, good. Thanks very much.
Oh, no problem.
Anybody else?
Just a comment. I found it fascinating, the way everything is named, sort of, all the references to the human beginnings, Lucy and
Oh, yeah.
Da Vinci. I mean, I think it would grab people's, help to grab their interest. I really like that.
Well, so this will burst your bubble a little bit then. I mentioned my instrument was called the Ralph, which was named, it's Lucy Ralph, which is named after New Horizons Ralph. Originally, the New Horizons mission had a UV visible IR instrument. I don't remember what it was called, but they decided that whole bandpass was too hard to design to all in one instrument. So they broke off the UV part and named it Alice. And so the scientist in charge of the remaining part was a big fan of the honeymooners. And so Alice is a big acronym for something. Ralph is named after Ralph Cramden. So sometimes it's lofty, and sometimes someone's just like, I like this name. We're going with this.
This is definitely lofty.
Yeah.
John, I have a question.
Yes, Mary.
Matt, this is Mary. I think you said that, do I have this right? The Lucy mission is for 7 years?
12.
12 years. Is there any chance that, like, if they happen to stumble upon any other Trojans, that they could extend the mission?
Yeah, so well, if you go back and look, so there are that first pass by the L4 swarm, we've kind of mapped out that area. We know the asteroids that are there. We're going to get to go see those 4. On the L5 swarm, we're going to pass that binary system, Patroclus and Menoetius. But at that point, like, we just kind of tail off. They don't know if there's anything else nearby that we're going to pass. But it's the end of mission then for us. So either we wait another 2 or 3 years to come back around and see if there's anything out there, but there's an opportunity there to do a thruster burn if we have enough fuel left and go target something else.
Okay, thank you very much. It was very interesting. Okay. Very interesting presentation.
Okay.
I have another question, if no one else does.
Actually, I do.
Go ahead then.
I have a quick question. Who was the exoplanet specialist you mentioned who was one of your leads on DAVINCI?
Jada Arney.
Okay, no one I've heard of. We worked a lot with Celts, so we know a lot of people.
Okay.
Okay, I'll go ahead then. To what extent is there competition for NASA Deep Space Network bandwidth among all these different probes that are going out?
So yeah, the Deep Space Network is it's a limited resource. It is managed by the Jet Propulsion Lab, but with priorities defined by NASA headquarters. So part of the competition process is we have to say, hey, based on this mission, we need this much DSN time at this rough amount of time, and headquarters commits to that as part of the competition and bid. So where one of the things they work with that regularly, though, is figuring out when you have time critical things that you absolutely need it, or when it's just like, hey, we need to downlink data at some point here. So when we do those flybys, we need some DSN contact right around those flybys just to check health and safety and do commanding. But all the pictures we're taking them, we've got 6 months that we can just downlink them at some point in those 6 months. So we'll be flexible with it then. During that probe mission, we'll need DSN coverage for that. But that's really 2 hard days of coast and 1 day or 1 hour of descent. And then once all that data is up on the spacecraft, we can take our time getting it back to Earth.
Okay, thank you.
By the way, if you ever get a chance to go out to the Jet Propulsion Lab, they have a artist in residence program, which is really awesome. So they have professional artists that come in and work on projects about stuff at the Jet Propulsion Lab. And in one of the lobbies, they have these vertical columns of LEDs that represent the different DSN ground stations. and you can see color coded when they're sending commands up a DSN pipe or getting data back down. And it'll actually, it's a live representation of what's going on. And then there's a little LED screen that shows which satellite it's talking to at any given time. It's a really cool way to kind of visualize that.
Yeah, super cool. Thank you.
Jose, you have your hand up?
Yes, man, I have to tell you, this is a great presentation. I really liked it a lot. I learned a lot. I have a couple questions about the communication of the system, like for DAVINCI and Lucy. What is the frequency range that NASA used to communicate with those systems? And the other question is, in the engineering respect, is how you interface all these multiple component sensors with the, I guess, with the main computer communication system in the systems. You know what I mean? To make them to talk to each other when you receive component from multiple vendors. You know what I mean? I guess that's a engineering challenge there.
Yeah, that's my whole systems job. So go to your first one. So typically, when you're talking to the Deep Space Network, we tend to prefer X-band. It's a little bit higher data rate than some of the other stuff you can do. I believe they also do, there are a few other bands that they'll use. We tend to prefer X-band. I should point out, actually, that probe, that when it's talking to the relay satellite, it's going to do S-band, which is a lower data rate than we would typically want. But it turns out it's one of the few that the atmosphere is transparent in. So, sometimes physics tells you what you have to do, whether you want to or not. In terms of how we get everything to work together, it's a combination. I mean, that is the discipline of systems engineering, is figuring out how to take a complex problem, decompose it into individual parts that a person or a small team can lead and develop in a way that they can easily be put back together and accomplish the thing you're looking for. So when you're talking about physically, like how you make sure that my LaRalph instrument's going to talk to the Lucy spacecraft, it's a combination of relying on good established standards, like SpaceWire, RS-422 communication buses, being very clear when you're writing out requirements, testing them and simulating them on both sides of the interface, and then setting up play dates. So a lot of times you're building engineering test units before you build your flight unit. So the absolute best thing you can do is have my ETU and the spacecraft ETU, plug them in and make sure they work, because any problems you find there, you can fix before you get to the flight build. So yeah, hopefully that kind of explains that. But yeah, the how you get everything to actually plug together and work and prove it, that's my whole job description. So
thank you so much.
No problem.
Anyone else? Looking for hands up.
Okay, I have another question then.
Go for it.
Who collects all these data? Which organization collects all this data from this satellite, and then which organization receive all this important data for study? I don't know, to analyze the data.
Yeah, so NASA actually, we are required by the federal government to make all of our data publicly available, which is a really good thing to see. So there's something called the PDS, it's Planetary Data System, that is a publicly available archive of all, I don't know if it's raw, but definitely all processed science data from all NASA planetary missions. So we will be required on both of these missions to deliver all of our data to the PDS, and there is someone there that makes sure that everything is maintained and made publicly available.
So if let's say would like to take a look at any of these data, how do we get hand on this data? Who do we contact, or is online? Or,
Yeah, I think you can just find it online, and it's a downloadable database. So yeah, if you're used to like looking up data for like a GIS mapping program, it's a similar type of thing of that. So there would be a kind of a README guide, some formatting instructions, and then just gobs of database you can download. The idea behind that whole approach is, we're going to collect the data for the science studies we want to do, but the real value comes when you make that data publicly available and let other people poke it and prod it and check their own, theories and hypotheses against the data you've taken.
okay, thank you.
What kind of bandwidth is available from the Deep Sky Network?
Honestly, I'm not going to be able to tell you that. I don't know. It does depend a lot on, so the thing to remember with these is that the main data bandwidth you're concerned about is the downlink. It's getting science data back to the Earth, not commands you're setting up or software loads are rare and don't take a lot of band.
Right.
So it's more driven by the antenna and the transmitter power that you have on the spacecraft. So for instance, and I unfortunately don't remember the data rates for Lucy, but they are low enough when we're out at Jupiter distances that one spectra from my instrument, the UV imaging spectrometer, which granted is a big data hog, but it can take 2 or 3 days to downlink. And that's why that AI image processing becomes so useful, is we're sending all the data, but if the spacecraft could say, hey, you took 100 megabytes of data, these are the 10 interesting 10 megabytes, then you can save on some of that downlink.
Is the data transfer done by schedule, or do you poll for it?
It is, the DSN time is scheduled, and then the operations team sends essentially playback commands within that scheduled DSN time. So we'll be told, hey, you're going to have DSN contact for an hour here, and the operations center will have queued up, play me image 1, image 2, and spectra 3 through 4. And that command will get uplinked, and then the spacecraft will respond.
What is the time to transmit to Jupiter and get a response, or one way? What is the latency?
I think that's on the order of a few minutes, but I don't know offhand.
Thank you.
No problem.
Yeah. I
Looks
have
like
another
somebody
question.
put it in the chat, a website that you can get this data from.
Oh,
Everybody
cool. That's
in the
what I
chat.
found it.
I'm hoping that's the right thing. And Ben put it in there. So just everybody take a look at the chat. You can take a look at it.
pds.nasa.gov. That sure sounds right. Yep.
So my question is about your spectrometer going with Lucy. Is it what sort of angular size does it record? Is it like a single object spectrometer, or is it more like an integral field spectrograph?
So it is, tell you what, let me share my screen because I can show you an example of what it is. It is a push broom imaging spectrometer. So give me a second to call this up and I can show you how it works. So what happens is, all right, let me share my screen. So the way you can picture this is it's a regular camera field of view or type rectangular field of view, and on top of it is a narrow bandpass filter, but it is the color it lets through varies as you go across the field of view. So, I don't know what that is. That's weird. So this is the New Horizons Ralph scanning across Pluto, and obviously made its false color because it was in near infrared. But what happens is if you track a part of the surface across the field of view, you essentially get how bright it is in each of these colors. And all of these dark bands, they're not issues with the field of view. They are absorption bands on the surface. So if you track a light thing across, you create a light curve for that point, and that gives you the spectral rate or spectral characteristics of that surface. So it is 80 microradians per pixel, and each pixel is about I think it's a 5 nanometer wavelength increment, to give you a sense of spectral angle resolution.
Okay, thank you.
No problem.
Okay. I think we can bring things to a close. Thank you so much, Matt. That was fabulous. Everybody.
Well, actually, one last quick thing to share with you. So,
please, yes.
When we did that flyby of Dinky, we took a bunch of images, and there are a few scientists who really love this structure from motion stuff. So they took these images as we flew by, and they were able to actually process them and create a 3D model of Dinkinesh as that. They're getting it set up in a printable model, so I can go have something on my desktop that is the asteroid we flew past. But one of the primary scientists who did that, who joined our team late, is Brian May, who you may also know as the guitarist for Queen. So I've never met the man. He's never shown up at Goddard, but I am on his team, which in my mind means I'm 2 degrees away from Freddie Mercury. So I'll take it.
Okay.
All right. Well, no, thank you all for having me. This was a good time.
Thank you. It was wonderful.
Yeah,
Yeah, thank you, Matt. Great job. Come
good
back
luck.
again.
Matt.
Nice. All right. We all have a nice evening. Enjoy your weekend.
Thank
you.
you. You too.
Bye-bye.
Bye.
Good night.
Kathy, I'll call you.
Hey,
Okay.
George, are we still streaming?
George?
Yes, we are.